Hello everybody. Today let's try to solve this distributed load problem. I picked it because it has a good recall to vectors and I think it would be just helpful to jog everybody's memory. So the question goes, the column is used to support the floor which exerts a force of 3,000 pounds on the top of the column. The effect of the soil pressure along its side is distributed as shown. Replace this loading by an equivalent resultant force and specify where it acts along the column measured from its base A. So I highlighted the key points of this problem. Column supports 3,000 pounds on the top, which is right here, and there's a distributed load on its side, which is right here. I also split the problem into two parts, part A and part B. The blue is part A, the red is part B. Replace this load by an equivalent resultant, and then specify where it's measured from base. So, anytime we have a distributed load problem, the first instinctive thing we should do is split up the shapes, which is going to be one rectangular distribution here and a triangular distribution here. Then from there, we have to find out each respective resultant force. And then later on, we can find the distance from the centroid with respect to the point that it's asking for. So here, from the rectangular distribution, we have at the centroid F1. And then from here, we have F2 in the triangular distribution. We remember these distances. This is going to be 1/3 of this distance x. And for the rectangular distribution, it's going to be 1/2. So let's find F1 first. F1 is going to be the area of this distribution over the span. So we have 80 pounds per feet over the span, 9 feet. Pretty simple so far. This is going to be 720 pounds. And then similarly, we repeat for F2. This is going to be, first of all, 1/2, because it's half the area of the triangle. We are going to take 200 minus the difference from the rectangular distribution, which is 80. And we're going to take the span again. And then that is going to give us 540 pounds. While we're at it, let's define x1 and x2. x1, x2. So we have x1, which is going to be equal to 1/2 the span. So that's going to be 4.5 feet. And then x2 is going to be 1/3 of the span. So since I'm already writing it, let's just finish the formula. We have 3 feet. Now we've solved for forces in the x direction, and we have a force in the y direction. How can we get a resultant force if we have two different opposing directions? Well, when we recall vectors, we know that we can look at our Cartesian plane and we can separate vectors into components. So we have f at x, which would be represented by an I, and then f at y, which would be represented by a j. Together, these components will form the vector fr, which is our resultant. And this is the vector quantity. Now, if we take the absolute value, we can get the magnitude of this resultant force, which is what we're going to need for a problem like this to simplify it into one singular number. So in our case, we have the square root of f of x squared plus fy squared. Pythagoras' theorem, kind of a recall to that too. So how are we going to use this? We have f at x and f at y. Don't believe me? They're right here. We have f at x, which is going to equal the summation of both of these. So what does that add up to? This is 1,260 pounds. And then we recall at the top, we have fy, which is 3,000 pounds. And now we can just plug these into our formula. So just to write it out for you guys, we have 1,260 squared plus 3,000 squared. Cool. This is going to give us 3,254 pounds. Around that, represented by a squiggle. And then we need to know kind of the orientation of this resultant force now. because it's no longer a vector. It's just a value. So we can represent its location by the angle theta. So theta, represented here, will be calculated as so. The tan inverse of 3,000 over 1,260. And that theta is going to equal 67.2 degrees. Now, how did I figure that out? Well, if we redraw our forces here, we can assume that the F at x is going to be like this. The F at y is going to be like this. And then here is the hypotenuse. We have FR. And this is just a simple SOHCAHTOA, and we're going to be using TOA. Alright, now we have everything set up from the previous part. Let's solve the next part of the problem where it says specify where the resultant force acts on the beam based on point A. So the resultant force is here. We need x. We can't solve for x with just units of force. So we have to remember that our equilibrium equations state that summation of moment will always equal 0. What does that mean for us? This means that the moment at A is going to be equivalent to force resultant times x. Very simple, right? It gets even better because we only need to consider force resultants at x. Why? Because the y component of this problem is lining up directly with point A, which means no rotation is being created at this point. It's acting directly on its axis. You're going to hear a lot of that when you get further on into the program. So we can solve this problem similarly as before, where we take moment at A over force resultant at x to solve for x. X is going to be equal to F1, 720 pounds, times X1, 4.5 feet. And what rotation is being created? This is counterclockwise. So this is going to be positive. Cool. Similarly with the other one, it's going to be positive as well. We have 450 pounds times x2, which is 3 feet. And then all of this is going to be divided by FR at x, which is 1260 pounds, which gives us our final answer of 3.86 feet. And that is how you solve this problem. I hope this helped.